Hello, in this video we will talk about collisions, the collisions of particles. Let's think about what happens when two cars collide. Well, there's usually a lot of noise, heat between the cars might deform. Some of this deformation might be permanent and some of it might just go back, kind of relax a little bit. Deformation, so some of that permanent. The cars might rotate, they will gain different post-collision velocities and rotational inertia. So the cars will change velocities and rotations, angular velocities post-collisions. So really, the collision of two cars is a very complicated process, still an active area of research, something that automotive companies have to deal with. However, in this lecture, we will consider a very simplified model of the collision of two particles. So here, we will consider a simplified, a very simple, maybe even the simplest, a simplified model for the collision of particles. And we have to be very clear about the assumptions we're making in our model. So first of all, we're modeling the impacting bodies, the impacting cars or bodies, whatever, as particles and not as rigid bodies. Okay, so model two impacting bodies of masses m1 and m2 as basically two particles of masses m1 and m2. Right? The second point is that what's the difference between bodies and particles? This means that we're neglecting the rotational inertia of the particles. So really we do not study how the particles or the bodies are going to rotate post collision. So we are neglecting the rotation, the rotational inertia, of the bodies. Okay? We can also, well, actually, this also means that geometrically the body might be a big object, but we're assuming that it is a particle. So we're looking at basically just a particle at the mass of the bodies concentrated at their centers of mass. Okay, so the all the mass going back to the previous point, if the body is not rotating, the particle even if you look at it or you think about it as like a bigger particle, like in this adjacent figure, all the points on the body have the same velocity. Okay, so this is here to the left, a kind of a model of what's happening with 4 collision stages: pre-collision, 2 compression, 3 restitution, and 4 post-collision. So pre-collision, the particles are just moving in the plane with velocities v1, v2, masses m1 and m2. Now, at 2 the particles collide. We can introduce the vectors n and t. So n is normal to the plane of impact. So this here we can think of this common tangent of the 2 planes as the plane of impact. Plane of impact. So t is tangent to the plane of impact. And n is normal to the plane of impact. The particles are going to stick together and they're going to start deforming until they reach a point of maximum deformation. So between 2 and 3, we have a point of maximum deformation. Maximum deformation. That's an intermediate stage. I can maybe call it 2 prime. They have a point of maximum deformation. Then the particles are gonna start to separate, start to kind of regain their shape, maybe not completely. That's the restitution phase until they completely separate in the post-collision phase. Okay? Another assumption we're gonna add is that during collision, all the forces acting on the particle are gonna be along the normal force, along the normal direction. So basically there is no friction, no forces along the tangential direction. So there is no friction between the particles. Okay, all the collision forces act along n, the normal direction. I'm also gonna introduce time instances t0, t1, and t2. Okay, so t0 is the time just before collision. So basically just before 2. T1 is the time at the end of collision. When we have the time at which we attain the maximum deformation. Okay, and then T2 is the time at the end of restitution, just before the particles separate. Time at end of restitution, just when particles start to separate. Okay, wow. So a lot of things going on so far. We've defined our stages of collision, introduced the times T0, T1, and T2 just before collision, during the maximum compression, and T2 just before you have post collision or separation after collision, and we're going through our assumptions. Okay, so let us see. Well, let us kind of look at the forces, draw the free body diagrams of the particles when they are in contact. So really here what we're doing is that we're looking at two time intervals kind of. T is between T0 and T1. That's compression, the interval at which compression is happening, and then T is between T1 and T2, and that's the interval where restitution is happening basically. So during compression, the particles are applying forces on each other. So basically compressive forces. Whereas during restitution, the particles are applying kind of restitutive forces are basically being applied. I'm not sure if we can think about it this way, but you can think of that there's a resultant restitutive force on each particle, and from our previous assumption there is no friction between the particles, so these forces are along n. So I'm gonna call these forces, so if this is particle 1, particle 2, particle 1, particle 2, these are the deformation forces, and these are the restitution forces. And then they are all along the, n. Okay, that is cool. Now we can write the linear impulse, linear momentum equation for each case. Okay, so then the integral from T1 to T2, well, shall we do that for each particle? Probably. Well, I drew the free body diagram of the two particles, but I just put the collision forces. There might be other forces acting on the particles due to basically just any external forces, weights, normals, just non-impulsive forces. So I'm gonna call them R1, R2, just R1 and R2. And these are just basically any normal way, just non-impact forces that don't have to do anything with the collisions. And we're assuming, let's add to our assumptions, that the collision times is very small. Let's assume that T1 minus T0 is very small. Sorry, not less than 0, less than 1. Oops. Yep. Between 0 and 1, less than 1. And also T2 minus T1 is less than 1. So these time intervals are very small really. Okay, so I can write the linear impulse, linear momentum equation for each particle. Linear impulse, linear momentum equation for each particle. Okay, so the integral between T1 and T2 and during each stage basically. So that's like A, B, C, D, each particle at each stage. T1, well, not T1 to T2 actually, T0 to T1 of F1d plus R1 dt, that's equal to basically the mass of particle 1 times the velocity of particle 1 when you have max deformation minus the velocity of particle 1 pre-collision. For B, that would be the integral from T0 to T1 of F2d plus R2 dt, which is equal to m2 v2 when you have the max collision minus v2 pre-collision. And then I can also write T1 to T2 F1r plus R1 plus R1 dt is equal to m1. Now v1 prime minus v1 max. v1 max, that's the velocity of mass 1 when you're at the maximum collision stage. And T1 to T2 of F2r plus R2 dt is equal to m2 v2 prime minus v2 max. Okay, now really we've already made the assumption that the collision intervals are very small, these assumptions, right? So when we integrate the smooth functions R1 and R2 over these very small intervals, the integral is going to be 0, so I can just get rid of these. Awesome. Another thing I can do is, if I consider the combined system in each case, then I can say that the integral from T0 to T1 of F1d plus F2d, that's dt, the linear momentum of the system during collision is conserved because the sum of the external forces is equal to 0. Now you might say, oh, but I have the other forces R1 and R2, but I'm just going to say that their linear impulse is too small because they're smooth and they're being integrated over a very small interval. So their linear impulse is 0, and the linear impulse of, so the linear momentum of the system is conserved. F1d and F2d, they will sum to 0 basically. Also the same thing happens during restitution. T1 to T2 F1r plus F2r dt is equal to 0. Okay? But basically F1d is equal to minus F2d and F1r is equal to minus F2r. Why are we doing all this? We're doing all this so that we can introduce the coefficient of restitution. Define a quantity, a scalar, the coefficient of restitution, E. E is equal to the integral from T1 to T2 of F1r dot n dt over F1d dot n dt from T1 to T2. So basically, that's the impulse of the restitutive forces over the impulse of the deformation forces. From these previous expressions here, we can write this in terms of the forces acting on particle 2 instead of particle 1. So I would just change the index to F2r dot n dt. Recall that these forces are all already along n, so we can project them along n. We're not introducing like any new phenomena, just getting basically the magnitude of these factors. T1 to T0 to T1. F2d F2d dot n dt. So let's think about this. If E equals to 1, what does that mean for E equals to 1? If E equals to 1, this means that the restitutive forces is equal to the deformation forces. The restitutive impulse is equal to the deformation impulse. So basically what's happening here is that whatever we've deformed, we've restored. This is by definition what we define to be an elastic collision. All the deformation is restored. On the flip side, if equals to 0, then the restitutive forces, the restitutive impulse is equal to 0. Then there is basically no restitution. No restitution. Basically, like the bodies, when they impact, they're like clay particles, and they're gonna come and they're gonna stick into one. Colliding particles become one, stick together to become one. Okay, now really in the real world, our coefficients of restitution are going to be somewhere in between. E is between 0 and 1. Now, yeah, when E is equal to 0, we call that a perfectly plastic collision. We have total complete deformation, no restitution at all. Now, in view of these impulses here, these impulses being written in terms of the velocities, we can get rid of this unknown v1 max and v2 max. Actually, we need to add one more assumption, that at maximum collision, at T1 maximum collision, the two particles, they're at rest with respect to each other in the normal direction. So the two particles along n, when they're both reaching maximum deformation, they're at this instant, they're not moving with respect to each other. They've really no more approaching each other, not yet going away from each other. Along n, they have the same velocity, which means that v1 max and v2 max, these are gonna be equal, basically equal. So in these equations, we can get rid of v1 max. So using basically this set of 4 equations and this set of 2 equations, we can write the coefficient of restitution E in terms of velocities. v2 prime dot n minus v1 prime dot n. Again, prime, as usual, denotes the post-collision quantities. So we can write the coefficient of restitution in terms of velocities. And this expression is more useful than the previous one, because usually in experiments what we observe is velocities. We really cannot measure the impact forces easily. Okay, so that's the coefficient of restitution. So far we've looked at the very complicated collision problem. We simplified it, we made a lot of assumptions, and we looked at the stages of collisions, and we were able to define this restitution coefficient. I'm gonna pause this video for now, and in the next video I'm gonna explain why we need to define this coefficient of restitution E.